All right, lecture 61, this is on torque. Torque is the rotational analog to force in linear motion. So linear motion we have force, angular motion we have torque. So if I imagine a generic rigid body, arbitrary shape, you can calculate its center of mass, and that is the point at which you can treat gravity as acting upon. Now if this is in free space, right, then this whole mass will just kind of accelerate downwards. You might think, well, what happens if, if I go out some distance r, let me make r a little bigger, r, and I'll draw in the opposite direction another distance r, we have a little mass element of this here. Of course gravity is pulling on that as well. I'll call this m sub I times r. But an equal distance in the opposite direction, you might also find a little m sub, we'll call it m sub j r, right? Yeah. So that the rotation that this little mass element getting pulled on by gravity, if we're in a uniform field, right? Uniform gravitational field, like near the surface of the Earth. I don't know why I can't speak today. This would induce a rotation, but of course you have a similar rotation being pulled on over here, right? And so it's just kind of a consequence of the center of mass that one of the things that it does is it balances all of this out. If there is an imbalance in the distribution of mass, it's going to find its way to the bottom. So I've kind of drawn it here such that it looks like a larger portion of the mass is down here somewhere, so it's going to roll around until it's at the bottom. And then once it's in that position and all the torques are all balanced out, it's going to stay like that until it hits the ground or whatever. But imagine that I now affix a rod right through the center of mass of this, or really anywhere through this rigid body. It's going to exert a normal force upward. It should be the same magnitude as, it's going to balance out gravity, right? So this is what happens when you fix this thing on a rod so that the rigid body is no longer falling, it's just sitting still, right? Yeah. And it's because the normal force from the rod at the attachment point is counteracting the rotation of the downward acceleration due to gravity. But now, however, right, well, let's explore that situation just a little bit. Let's say that there's more mass on this side, right? So I'll kind of extend my body out, right? Give it a little more mass over here. Now it's a little bit like a teeter-totter, right? I call it a teeter-totter again. Well, what is it called? Seesaw. Seesaw. Seesaw, right? So remember the seesaw from, here's the balance point, right? So if I want to lift a big mass using a smaller mass, I can take advantage of lever arms. So I'll call this Li. Actually, I'm going to call this, here's how I'm going to label it. I'm going to label this as m sub I times g, and this I'll label as m sub O times g, because this is what I'm going to call the output side, okay? So if I want to lift this guy up this distance, delta x output, right, I can do so with a smaller mass as long as our input side is longer than our output side. You might remember this from lecture 44 on simple machines, right? We talked about the mechanical advantage that you get in a leveraged situation like this, right? And it was, in this case, it's going to be, I think it's delta x input divided by delta x output, right? So I have to move this a pretty far distance, right? But I'm applying a relatively small force because the input mass is, say, a smaller mass, right? I'm taking advantage of this lever arm. So whatever this force is, right, call it the input force, it is smaller than the output force, right? Yeah. Because it would take a lot of force to lift a heavy mass, right? It would take the mass of the object times g. That's the amount of force it would take. But with a lever arm, right, in this simple machine, I can lift it using a smaller force by taking advantage of a longer lever arm, okay? Okay. So I think that's right. The mechanical advantage should be a positive number, so this will be the smaller value, this will be the bigger value, so this will be, yes, I think that's the right ratio. And I'll remind you that the way this worked, right, is we said, well, it's a force multiplier, these simple machines. It's not an energy multiplier or a work multiplier, okay? You're going to get out exactly the same amount of work as you put in, right? So how much work do I do on the input side? Well, I apply a smaller force, F sub I, but over a longer distance, R sub I, right? And that's going to be equal exactly, remember that work is force times distance, okay? So we're assuming this is a constant force that we're applying. So this will be equal to the output force times this smaller output distance here. The work that we're doing is exactly the same, right? You don't get energy for free, but you can multiply the force of something by using a smaller force and moving something over a larger distance. But let's look at this quantity. So what is this quantity here, right? We have this force times a distance. Now the force that you apply, you want it to be in the direction, right, that's useful. For example, with this case here, if I would apply the force in the radial direction, so away from the lever arm, right, would that do any good? Am I gonna, if I get a pry bar and try to, pry something up that's heavy, it doesn't do any good for me to stick it in there and then pull on it. Then it's just gonna pull out. Maybe I push on it, so I push inward. Is that gonna do anything? Not really. You want to push downward, right?
Yeah.
So the force that you apply needs to be perpendicular to the lever arm, okay? And so for that, just like when we talked about momentum, or angular momentum, the only thing that's going to contribute to the rotational velocity of something, or the rotational motion of something, is a tangential velocity. Similarly, only a tangential force, right, is going to contribute to rotating something. I mean, here we're kind of rotating. It's not exactly the same thing, okay?
Okay.
But let's go back to this situation, where now I'm going to apply a force, over here perhaps, right? Well, I guess we can just say I'm going to apply a force here, F, right? It's going to create a rotation, okay? You can see if I pull on this side and it's fixed here, it's going to rotate, right?
Yeah.
So now I'm assuming that I'm no longer maybe in a gravitational field or anything, and so there are no external forces acting on it, and I just apply a force here. It's going to rotate it about this axis, right? We're going to get a rotation motion in that direction, right? So the only thing that's going to contribute to it is the tangential component of that force. If I try to pull it this way, right, any force in this direction, right, that's a radial force, is not going to do any good. So if I apply some general force, right, it's only the tangential component which is going to contribute to the rotation, okay? And so we can think of this force times this lever arm, this distance, all the way to here, right, R, as our torque. Usually we use the Greek letter tau to express torque, okay?
Okay.
So it's the tangential force times the distance from the rotational axis, okay, directly, that affects this. So for example, if I wanted to compute the torque at this point here, now the distance to it would be a line like this, you see? Make sense?
Yeah.
And the force that I want to apply to rotate it would have to be perpendicular to that, okay, or tangential to the motion, okay?
Okay.
Like angular momentum, right, torque is a vector. Well, even like force, torque is a vector, right?
Yes.
Because force, well, in this case it's in a particular direction, but here's, a direction as well, right?
Yes.
And the vector quantity of torque, so that's the vector, is equal to R cross F. So here's F. It's going to automatically pick out that tangential component, just like we did with angular momentum, right?
Yes.
So it's going to be R times the magnitude of the magnitude of R times the magnitude of this times the sine of the angle between them, between R and F, right? Which is going to be this angle over here, actually, right? And in what direction is it? Well, it's called the right-hand rule. And I think, did we talk about the right-hand rule with angular momentum? I think we did. This crossed with this, right? So if this is, say, R, and this is, say, F, well, let me do it the other way around so I don't want my thumb coming out. This is R, let's say, and this is F, okay? The way I figure out which direction, what the direction of this is, because it'll be perpendicular to both the direction of R and the direction of F. So I take my hands and I curl R into F, and whichever way my thumb is pointed, that's the direction. If I apply a force over here, let's say, here's R, here's F, I curve it in, and I get a torque which is coming out. So the units of torque are the same as the units of energy. They're Newton meters. Remember that newtons are the units of force, meters are the units of distance, and force times distance is energy, and we usually call that a joule. But we won't call these joules, we'll call them Newton meters. So let me now write down, now that we have an equation for the torque, let's relate it to the angular units that we talked about in the previous couple of lectures. This is the vector quantity, but let's not worry about that right now. Let's worry about just the tangential force, right? Which is going to be a mass times an acceleration, which is in the tangential direction, yes?
Yes.
There's a, from the relation S equals r theta, well, that's arc length, right? We can also get a relationship for the tangential component of the acceleration, which is going to be equal to r times alpha. Similarly, the tangential velocity is r times omega, right? The angular velocity. So we can substitute this relationship in here. It gives me mass times r times alpha. Now the torque, which was the tangential force, times r, the radial distance from the rotation axis, this is going to be equal to mass times r squared times alpha. And you might recall that I, for an individual piece of mass, right,
Yeah.
is equal to the mass times the distance squared from the rotational axis, right?
Yes.
So this mr squared, we can write torque is equal to I alpha. And this is completely analogous to F equals ma, right? So let's look at those two, right? So here we have the linear version, force, right?
Yes.
In terms of the mass and the linear acceleration. And then we have the rotational. The torque is equal to I, which is the moment of inertia, which is kind of the analog to mass for a rotational system, times alpha, the rotational acceleration. So you see they're very similar in this way. So we can write over here, I'll write N2 for Newton's second law, F equals ma, and tau equals I alpha. So let's use it just a little bit. Let me draw a system for us to consider. And we're going to be applying a rotation like this. And we're going to do it by tying a rope around this guy. We'll tether it to the side of the disc. It'll curl around the backside. And then come out over here. And we're going to put tension on this rope. Now put a tension of 1 Newton on this rope, right? So I'm pulling on the rope. What's it going to do? Of course it's going to rotate the disc, yeah?
Yeah.
But the disc is going to resist rotating because it has rotational inertia, which we call the moment of inertia, right? So for this particular disc, you might recall that I is equal to 1/2 mass of the disc times r squared, where r is the distance, the radius of the disc, right?
Yes.
Just a property of a cylinder like this, a solid cylinder. If it was a hollow cylinder, you might recall it would be equal to just mr squared. And so my first question is, you know, not V, I want omega. What is omega equal to, right? Well, how are we going to figure that out? Well, we can use the sum of the torques. We can use Newton's second law, right? There's only one torque acting on this, right? So the sum of the torques is just equal to this 1 Newton times r. Well, I need to specify r, don't I? Let's let r be equal to 1. R equals 1 times 1 meter. So that's 1 Newton meter of torque. Okay? Now you might recall that oh, I'm sorry, I've gotten ahead of myself. So this should be equal to, right, I alpha, right? This is equal to I alpha. Well, I is 1/2 mr squared. Well, that's just 1/2. We need a mass too now, huh? Mass, we'll let that be 2 kilograms. Okay? So that's 1/2 times 2 kilograms times r squared. That's, 1 squared meters squared times alpha. So I can solve for alpha. Alpha equals, that's going to cancel there. This is obviously going to just equal to 1. So that's 1 radian per second squared. So we have an acceleration of 1 radian per second squared. Okay?
Okay.
Remember, 1 radian is about in the order of about 57 degrees, I think. Okay, what next? That's omega. Oh, that's alpha. I'm sorry, we haven't gotten omega yet. Getting ahead of myself. So now we have alpha. We can use a kinematic equation, omega equals omega naught, plus alpha times t, to figure out, let's say omega at 2 seconds equals question mark. So let's figure out what omega at 2 seconds is. Well, let's let omega not be equal to 0, so it's not moving initially, right? And so omega at 2 seconds is going to be equal to just alpha, which is 1 radian per second squared times time of 2 seconds. So that's going to be equal to 2 radians per second. So that's omega. Okay?
Okay.
So we can fill that in over here. Let me write this in purple, the questions. Omega, 2 seconds equals 2 radians per second. Okay? Does that make sense? Just a kinematic equation, taking advantage of this constant acceleration because of this constant tension we put on there. All right, another question we can ask is, well, what is the angular momentum at this time? We'll say L at 2 seconds. Well, angular momentum, L, is just I omega, right?
Yes.
And so all we need to do is substitute in for I, which I think we've already calculated before, but it's 1/2 times 2 kilograms times 1 squared, so that's going to just be 1. Because it's kilograms meters squared, okay?
All right.
Times omega, which we just calculated, which is 2 radians per second. Now we usually, when we have mixed units like this, if it's not just radians per second, but like kilogram meters squared radians per second, then we'll just drop the radians and just say the answer is 2 kilogram meters squared per second. And let's write that result over here. 2 kilogram meters squared per second. I know the units are kind of wonky, but so another question we might ask is, how far does this rotate in these 2 seconds, right? So that's another kinematic equation. That's asking, well, what is theta, the angle that it's rotated, right? It's going to rotate some angle theta in this time, right? Theta after 2 seconds, what's that equal to? Okay, we want to know what theta is after 2 seconds, right? That's how far it's rotated. We can just use a kinematic equation. So we have that theta of t will be equal to theta naught, which will let be 0, plus omega naught times t, but we already said omega naught was 0 before when we calculated omega, so that would be 0, plus 1/2 alpha t squared. So we already have alpha, that's 1 radian per second squared, so that's going to be equal to 1/2 t squared. So theta, the angle that we rotate after 2 seconds, so theta of 2 seconds, is going to be equal to 1/2 times 2 squared is 4. That's second squared. Well, we have units of radians per second squared, so this will just be radians. So that is 2 radians, which is approximately 115 degrees. Okay?
Okay.
So what other quantities can we calculate that's useful? What about work? Right? We haven't really talked about work, but if when you apply a force over a distance, you're doing work. I must be doing work if I can apply a torque over a rotation, right? So they are kind of analogous. So first let me put this up here. This is 2 radians. What about work? So I'll write over here. Work. So work is equal to F, the tangential force, times some delta S, which must be equal to a torque times some delta theta. Well, we already have the delta theta, right? We already have the torque, right? The torque is 1 Newton meter. That's tension, sorry. 1 Newton meter. We calculated that here. And delta theta, right? We went from theta being equal to 0 to theta being equal to 2 radians, right? So the work that we've done in this 2 seconds is just equal to the torque, which was 1 Newton meter, times 2 radians, so that's 2 joules. And finally, power, another analog. Well, it's not really an analog, it's just the power applied to this. But so power is the change, the work that you do in a given time interval. And so this, if I replace delta W with the torque times delta theta, and then divide that by delta t, well, delta theta over delta t, that's just the definition of the angular velocity. So that is equal to tau times omega. I can write the tau a little nicer, I think. Tau times omega. So here we've got, not all analogs, but the application of both work and power. So what's the power from this? Well, power after 2 seconds at that tension is going to be equal to the torque, which is 1 Newton meter, times omega, which we calculated is 2 radians per second. So that's going to be 2 watts. And watts is the right unit to use, okay?
Okay.
Because we've used all SI units here. We used radians, we used newtons, we used meters, and we used kilograms. So we'll get an answer that's in watts. I think that's all it's going to show on torque. We'll use it again, but I want to do one more lesson on the conservation of angular momentum, okay?
Okay.
And maybe we'll talk about gyroscopes. I'd like to, but I don't know that we will. But we'll definitely talk about angular momentum, and we'll do maybe a ladder calculation. That way we can talk about friction. So you put a ladder up against a wall, you know, it doesn't fall. It's a statics problem. Remember when we talked about statics, right?
Yeah.
Things that are not moving, right? This is a statics problem involving torques. And so if you ever do any engineering, in particular statics, then torques play a big part of it, because not all the forces are just linear forces. Okay, well, I think that is it. So let's wrap it up.
See you next time. See you next time. Yeah.